Yeah, my name's Keshav. I work at Google, software engineer on the TensorFlow Extended TFX team. I want to thank my colleague Robert Crow. The slides were created by him, so thank you too much for him. Let's get started. I know we had 2 talks on MLOps this morning, so half my talk is kind of motivation on MLOps. We'll try to breeze through that so we can get more into the specifics on how TFX works and why your company might want to use TFX. Let's do a quick exercise. I think everyone in this room is familiar with supervised ML, so this should be quick, right? Let's pretend we're training a model. This is a gecko. This is a chameleon. Gecko. Chameleon. Gecko. Chameleon. Okay, cool. That's enough training. I think that's enough data. At this point, what does an ML researcher do? They say, okay, cool, we've trained our model. It's time to predict. This is also known as inference, so we can do some of that. Gecko, chameleon.
Gecko.
Yeah, good. Gecko, chameleon.
Chameleon.
Gecko, chameleon.
I think I'm good at ML.
Awesome. If we're doing it in software, we would hopefully use TensorFlow. We might use Keras. We could use something like the fashion M1IST data set. This is probably in every beginner tutorial. I think Margaret was mentioning this in her talk as well. And you'll do a basic, like an ML 101 kind of situation. You'll predict, what is the type of clothing based on options here, right? And if you're just a student in school, great, you turn in your assignment, you'll never think about that code again. If you're a researcher, you'll take it one step further. You'll publish, maybe even publish in NIPS, right, like the BERT model. But even then, you're probably done. But let's say you're an engineer and you have a product, and ML is a big part of that product. And you want to deploy your model in production. There's a lot of steps beyond an ML model. And so I'm going to try to motivate MLOps, what it is, why do we need it. So we'll skip through. I know that we had 2 talks this morning. So 2 big reasons, right? Change and process. So the first reason you need MLOps is something has changed. So imagine an environment where training serving skew, like Luck was talking about, that's very common. And this is pretty common that we've seen in online retailers with recommendation systems, for example, right? So something in the model, something in the environment changes and your model hasn't been trained. We can do a thought experiment, right? You're an online retailer, you're selling shoes, you have a model that predicts your click-through rate. And based on that prediction, you decide, okay, I want this much inventory. Suddenly, it's springtime and your model has really dropped on men's dress shoes. You just don't know why, right? Why? Why is my model working worse? How do we even know there's a problem, right? So how would I know that my model has started performing poorly? And what's going to end up happening is you would know because as a business you've ordered way too many shoes, or you've ordered not enough, right? And this is probably the worst way you want to find out as a business that you've messed up. You've bought hundreds of thousands of dollars worth of shoes, or you haven't bought enough shoes and your customers are unhappy, right? And if you don't have MLOps in place, any way to tell that this training serving skew has happened, you'll never know. And this is one motivation, change, for needing MLOps. If we think back to our original, that quick exercise we did, is this a gecko or a chameleon? It's kind of hard to tell. It's a gecko, satanic tail-leafed gecko, right? And this is just one example of when your model's out in the wild, in production, of things that can happen and that can have business impact. And kind of the second motivating factor for why you want MLOps is process. You want a robust engineering process in place. Right, so for prod ML, there's 2 parts. First, you have all the steps you need to create your ML model, right? This is your labeled data, you're looking at dimensionality, you're making sure it's a representative data set, and all that jazz, right? Latest network architecture. But if you remember, we're a company that wants to put ML in our products, so we need all the modern software development toolkits. So we need testing, reliability, monitoring, all these steps. So if we're doing ML ops, we need both things. We need ML development and we need modern software development. So we'll just skim through this definition. There's a lot of definitions out there. We heard a couple today. This is one that I particularly like. I think Luck actually mentioned this one. And we'll look at that second sentence. Practicing ML ops means that you advocate for automation and monitoring at all steps of ML system construction. And this includes integration, testing, release, deployment, and infrastructure management. Right. So the ML system development is the dev, the ML system operation is the ops, hence MLOps. And we borrow a lot of terminology from DevOps, for example, continuous integration. But when we're thinking about MLOps, continuous integration has a few different parts. We want to test and validate our code and our components, but we also want to test and validate our data, our data schemas and our models. And if we think about continuous deployment, it has a slightly different meaning. It's not just about a single software package or service, but your entire system, which is in this case an ML training pipeline. And this training pipeline should be automatically deployed to another service, a model prediction service. And there's kind of a third step. So we're all familiar with CI/CD. In MLOps, there's continuous training as well that you might need. It's a new process. It's unique to ML systems. And the idea here is that you're automatically and you're always gathering new data, retraining your model, and you're serving new models. So let's take a step back and think about what a data science team at a company might look like, right? They're able to come to you and they can recreate the latest paper and it serves your business use case. Awesome. But then, if the business comes and says, hey, we need this model in production. And what they do is they probably have a manual script for each one of these boxes. So if we just go left to right, you have your data extraction, data preparation, you train your model. Great, you have a trained model. You save that model in some registry, and then finally you serve that model. And MLOps at level 0 is kind of what happens when all these things are ad hoc. And Lokita gave a great talk this morning where he talked about how, for a lot of people, a lot of companies, a lot of teams, this level where every system is manual, maybe your model only needs to be deployed or retrained twice a year, it's okay to have a manual script. But if you think about systems that are dealing with millions of active users, or recommendation systems, systems that really, where ML, messing up the ML model is gonna maybe cost you millions in revenue, then you need something a bit more robust. And that's where I would argue that MLOps is useful. So I can talk about what we do at Google. We use a tool called TensorFlow Extended. This is also open source, so if you Google it, you'll find the repo and a whole host of tutorials. And as I'm sure all of you know, all of our products have some ML baked in somewhere. So our flagship products, Chrome, Maps, Search, they have pipelines running on TensorFlow Extended, TFX. Our other bets companies, Waymo, Verily, so on, they also are using TFX. And then over on the right, you'll notice that our Google Cloud AI products, a lot of them, what they do is, especially with Vertex AI, they'll build on top of TFX, and then a client, the public, a third-party client will typically use Vertex AI, for example, and under the hood, it's using TFX pipelines. So let's talk a little bit about what TFX looks like and what different production components look like. So at the top in the gray, you have all the steps of a good ML pipeline. In the middle, in the white, you have different TensorFlow flavors that we use to achieve that. And in the bottom, the orange, you have different components. So we can do a really quick run through. So for data ingestion, we have an example gen component. This reads your data and this ends up writing TF examples output. For data validation, we have a component statistics gen. This generates summary statistics about your data. We have a schema gen. This can generate a schema about your data. And we have an example validator. This is something that can be used for training serving skew, schema skew, things like that. Finally, we have feature engineering. So you can encapsulate, transform any feature engineering that you want to do, assuming your model needs it. You have training components, a trainer and a tuner. You can validate your model with an evaluator. We also have an infra validator, which is interesting. This checks that your model is in the correct format and would run in a mock production environment. We have a pusher, so it pushes your model somewhere. And then finally, you have your bulk inference that actually performs the inference with a trained model, and you have some server, some way you serve that model. And these are kind of the different components that a TFX user can string together to come up with an ML pipeline. So this pipeline is kind of the hello world of TFX, and there's kind of three parts. The top pipeline in orange, that's our ML training pipeline. And this has all those components we talked about, ingesting the data, transforming it, it's generating summary statistics, and so on. And then over here on the right, you see 4 different options of serving your model. You can push the model somewhere to TensorFlow Hub. If you're doing a web development, a web application, you can use TensorFlow JS. If it's on mobile, TensorFlow Lite. If it's an online or batch processing you can use TensorFlow serving. And at the bottom in green, that's going to be your inference pipeline. So it's going to have just read the examples, use your trained model, and perform bulk inference based on that. So this is pretty typical of a TFX workflow. You'll have one training pipeline, and then you'll have one use like evaluation or a batch inference pipeline. Rather. Okay, so we've talked a bit about what different TFX components are. Let's go a bit more in depth. How does a component work? There's three parts. There's a driver, an executor, and a publisher. The driver coordinates job execution. The executor actually performs the work. This is probably where some of your custom code, for example, a training component would go. That training load for I and how many epochs. And the publisher updates some ML metadata storage, some artifacts produced. Now, if you're a TFX user, you're probably going to end up changing the executor. You probably won't change the driver and publisher. That's mainly boilerplate code. Let's take a bit closer look at a single component. So the component's in orange, and at the top you'll see a config file. This is where you'll specify, some details about how you want the component to run. And then you'll notice that there's a metadata store, this circle at the bottom. So the component will read some input artifacts from this store, and after the component has performed its work, it's going to write output artifacts to this metadata store. So because we have this metadata store, you can perform artifact tracking for all steps of the pipeline. If you want to try this out, it's pretty simple. We offer TFS orchestration directly in a notebook. So if you want interactive and experimental development, you can spin up, a Colab notebook, Jupyter notebook, and try out what this pipeline would look like. There's something called an interactive context that you would just set, and then eventually you can run that basic pipeline on your laptop using that interactive context. Although if you're in a production environment, you probably would use Airflow, Kubeflow, or something similar. Let's go a little bit in depth about the metadata store. What's it doing? How does it work? So what's in a metadata store? The primary thing that's in there are the types of artifacts and the definitions of their properties. So one obvious artifact example is the trained models that are produced every time your pipeline runs. And you probably want to store every single model that was produced. If your pipeline is retrained every 15 minutes or every hour, you want to keep track of those trained models. It also stores records of runs of each component. So in this case, we would have the trained model, and we would also have the trainer run that produced that model. Now, why is this important? It's because we can have data provenance across all executions. So this morning, a couple times, we heard an example of, maybe 3 years later, someone comes to you, a client comes to you and says, hey, you denied me a loan 3 years ago. You want to figure out the data provenance as to what was going on at that time. The metadata store world, you can recreate that data and understand what examples were used to train that specific model. Let's talk a little bit about Apache Beam and distributed pipeline processing. And this is kind of how each component runs under the hood, the executor part of each component. What is Apache Beam? It's a batch and streaming distributed processing API. So a user in an SDK frontend can write some Beam pipeline in Java, Python, whatever. And then there's something called runners, which actually execute the Beam jobs on the distributed cluster. There's a lot of options, Apache Samza, Google Cloud Dataflow, Flink, Spark, and so on. So these are the runners on the right. And on the left, you'll notice that that's how you would write a Beam pipeline. Very basic. This pipeline is trying to sum all the numbers based on a certain key. That's your Beam pipeline definition in different languages. You can then send that Beam pipeline to whatever distributed runner and then run that pipeline. So how do TFX components actually use Beam? Well, again, on the left is your TFX component with the executor, and on the right is your processing cluster. Your executor will write a Beam pipeline. The Beam pipeline is translated and sent to the processing cluster on your runner. Some result is returned. And then finally, that result is translated, sent back to the executor, and then something ends up being written to that metadata store that we talked about. Another interesting use case we see inside Google as well as with a lot of third-party users is custom components. A lot of times a user has a pipeline and they need a component that performs some custom processing, some custom evaluation, whatever the need may be. And this is possible with TFX. There's 3 ways to create a custom component. The first is using a Python function with decorators and annotations. The second is a component that has maybe a Docker container somewhere. And the third is you can extend any existing components, standard components that we provide in our open source library. If you create your own component, you still get all the benefits of a TFX pipeline. This includes metadata management, lineage, pipeline monitoring. So this is something we see a lot of third-party users really excited by when you use TFX. And in this case, the custom component is that little gray box at the right side of the pipeline. Here's just a quick example of how a user could make a custom Python component. You would write your component definition up here, def my component. You'd add this little decorator, add component. You'd specify the inputs, maybe your model, the accuracy threshold, and so on. And then here you would actually write some component code that does what your custom component wants. If you have a container-based component, it's very, very similar. The difference here is that you'll specify what image you want to read from, the command to run inside the image, and so on. But essentially, it's a very similar idea as a Python-based component. You'll end up configuring the inputs, the outputs, the parameters, and the Docker image, or whatever image. So we talked a bit about MLOps. We gave some motivation, hopefully. We talked a bit about TFX, how it works. Let's take a look at what some third-party users are doing with TFX. One of our earliest adopters of TFX was Spotify, actually. So before TFX, all their MLOps was done in custom Scala code. And then they realized, hey, our data scientists inside the company, as well as outside the company, they all use Python. And a lot of the tool sets that Spotify had built up custom, that MLOps level 0, they weren't used anywhere else. They were one-off, but dirty, hacky solutions. So they became a very early adopter of TFX. And there's a blog post at the bottom, but you can find online. But one of the nice quotes that was in there, in fact, early analysis indicates some teams are producing as much as 7x more experiments. And on the right, you can just see a graph. The red is the number of development pipelines. The blue is the number of production pipelines. The bottom is a span of roughly 3 months. After they had their TFX integrated to their stack, they, in some cases, they almost 7x'd the number of pipelines they're running. And this is a common theme we've noticed across third-party users of TFX. What they've mentioned to us is, yes, there's a startup cost of migrating your stack to maybe GCP, Vertex AI, or even just TFX. But what happens is that the data scientist team is able to really, really quickly iterate, focus on the network architecture, and then not really worry about what's going on in production. And that's one of the real benefits we see of TFX. Teams quickly iterate, and they can quickly move a new model into production. Let's take a look at Waze. So as you all know, Waze is the world's largest community-based traffic and navigation app. If we think about some of their ML challenges, in terms of modeling, there's a few use cases they have. One, they want to predict ETAs, they want to match riders and drivers, they want to serve the right ads. And the challenges they have is that they have large-scale geospatial data, and they have a real-time latency need. So they had some criteria for a solution. It had to be simple, it had to be managed, they didn't want to deal with servers or hardware. It had to be customizable just enough so they could capture a tail 5 end of their use cases. It had to be scalable, so that means horizontal, vertical scaling. They also wanted to be Pythonic, again, to match the larger ML community. And what they ended up doing was they had TFX on a Vertex AI pipeline powered by GCP. So on the right, you'll see this green pyramid. They might be hard to see for the people in the back, so I'll just talk through it. At the bottom of the pyramid is Vertex AI, and this is the fully managed ML platform that the Waze people would use, or sorry, that's running under the hood. And then on top of that, you have TFX. This is the ML pipeline that we just talked about, those orange components. And at the very tip of the pyramid is they have their own software package called Waze Data TFX. So what their data scientist workflow became now, if they wanted to push a new model to production, they'll fork, maybe they'll change a config somewhere, maybe they'll add a new layer, they'll add some regular layer, whatever, they'll tweak the code, and then they can deploy. And once it's deployed, it sets up continuous training. It sets up a pipeline with all the TFX and Vertex AI magic. You get all the GCP goodies, and they're able to do it. The data scientists are able to iterate much, much faster, okay, like we talked about. The third example we'll talk about, and the last example, is called Digitech Galaxis. I actually wasn't familiar until I read the blog about these folks. They're the largest online retailer in Switzerland. So they sell clothing, electronics, everything, you name it. And their main thing was they had newsletters that they wanted to personalize to 2 million users every week. And the issue is they had 12 different recommendation systems. And they wanted to determine, which recommendation system should I use for which user. And the way to do it is contextual bandits. You can look it up. It's essentially just, you can think of it as a black box component for now. They also had a really big latency requirement. They needed sub 50 millisecond latency. And finally, again, like we saw with other people, they wanted something that's end-to-end, easy to maintain, and generalizable to other use cases. Again, tail-end customizability. So this is kind of their contextual bandit model. On the left are the context features. You have your actual model that performs the context bandit, the contextual bandit model. And what happens is it selects one of the 12 recommenders for that. And based on that recommender, it populates the newsletter that the user would see, and there's some reward calculation. A positive reward if the user clicks on the newsletter, the link in the thing. A negative one maybe if they unsubscribe. And this kind of framework is pretty common with contextual bandits. What's important here, though, is that they ended up using, again, Vertex AI pipelines, which under the hood also had TFX run. And we're not going to talk through the specifics here, but this was their ML training pipeline, and this was their ML inference pipeline. So if we kind of circle back to the central question, why do we need MLOps? What's the motivation? The two big reasons are change. Right? Something in the environment has changed, and our model really needs to know about that change. And the second is we want to have a robust engineering process that can actually speed up our model iteration time. If you want more information, TFX is open source. There's a whole host of links for you up there. Big community around this, so feel free to check any of these out. Thanks so much. Happy to take any questions.
Okay, yeah, any questions? Yeah, if you have questions, you can raise hand. I have the mic. Oh, everything is clear as a map?
I think there's one in the back. Or no?
Oh, is there?
Yeah.
Okay, yeah, maybe you can just, oh. Sorry. Yeah, I got it.
What is contextual bandits?
Say that again. Oh, what is contextual bandits? Yeah, so I kind of breezed through it. The main idea is here, right? So the contextual bandit box here, imagine you have some layers of neural nets in there. And what it does is it'll help you pick some recommender system, right? And then based on what's picked, you'll end up populating that newsletter with the recommenders from that specific. Like, so if the contextual bandit model, it picks 3, then the newsletter will populate recommendations based on 3. And then you can get some reward, right? Did the user click on that? Positive reward. If the user unsubscribed from your newsletter because it's too clickbaity, negative reward.